Okay, so in the last lecture we discussed the concept of Fourier series, and also we have evaluated the Fourier coefficients an and bn. How to evaluate an and bn? Okay, these two are required to set up the Fourier series. Like we said, if x of t is periodic, then x of t plus t naught, x of t is equal to x of t plus t naught, and then x of t can be written as a naught, a constant term, sigma n is equal to 1 to infinity a n cosine of n omega naught t plus sigma n is equal to 1 to infinity b n sine of n omega naught t, and a naught is the average value, that is 1 over t naught integral of 0 to t naught x of t times dt, and then a n is equal to 1 by t naught times average value of x of t, 2 times average value of x of t naught times cosine of n omega naught t. Please recall this definition. So this is simply 2 over t naught integral of 0 to t naught x of t multiplied by cos of n omega naught t, then bn is equal to, by the same formula, but now here x of t is multiplied by not cos n omega naught t, but sin n omega naught t times dt 0 to t. Okay, so these are the procedures that we need to follow. So for a given waveform you have to calculate, for a given periodic waveform you have to calculate what is a naught and an and bn. But surprisingly, there are situations, in fact many situations, where we don't want to calculate all these three, a naught, an, bn and all. Certain waveforms this bn will be 0, for certain waveforms an and a naught is equal to 0. So there are something called symmetry conditions. If by looking at the waveform you will come to know what kind of symmetry does it have, and based on that you need to calculate only a particular coefficients, not necessary to calculate all the coefficients. That's what we are going to see. Okay, so in many situations the waveforms that we have to deal with exhibit certain types of symmetry. Okay, real waveforms exhibits certain types of symmetry. Okay, so in which we can take advantage of and simplify the work involved in evaluation of these Fourier coefficients. So if you have certain kind of symmetry, then no need to calculate like a naught, an, then bn, all these three. It is sufficient to calculate any one. So let us see what are the things that we are going to calculate and what are the things no need to calculate. So this we will now take up for study under the being symmetry conditions. Okay, so there are 4 symmetry conditions that we are going to consider here. So this will simplify our life. No need to calculate all the coefficients. Okay, so let's talk about 4 kinds of symmetry and then see how each individual set gives rise to some of advantages in the matter of evaluation of Fourier coefficients. To start with, suppose we are given a function which is an even function of time. First of all, to find Fourier coefficients, the function should be periodic, that is the first thing. Now this is periodic as well as even function. That means the definition of an even function is x of t equals x of t plus capital T naught sorry, this is for periodic, okay, I am sorry. X of minus t for all t. This is a function definition for even functions. That means what? You have the function like this, let us say it is going like this. Like this. So, this is an example of even function, x of t is equal to x of minus t. Okay, here the function varies in this manner. So, this is an example of periodic waveform, as well as this is the even function, and let us say the basic period is t naught. Okay, so this is periodic. If it is not periodic, then you cannot take Fourier series. Okay, so first periodic, and also it is an even function. So, as I said, the Fourier series is like x of t is equal to a naught plus sigma n is equal to 1 to infinity a n. I am repeatedly writing this formula so that you can keep in your mind, so that you will not forget. Cos of n omega naught t plus sigma n is equal to 1 to infinity b n sin n omega naught t. Now, we said a naught is constant. Okay, it maintains its value. So, we will consider that to be an even function, x of t to be an even function. So, what about in this expression? See, this is an even function, let us assume, and this a naught is a constant, no problem. And what about this guy in terms of t? Okay, so this I need not to bother about a naught and a n and b n. Why? They are all constants. Okay, so I need to look at only this guy and this guy now. Now, this cos n omega naught t is an even function, right? Cos of minus of n omega naught t minus of t is equal to cos of minus n omega naught t, which is equal to again cos n omega naught t. But what about sine function? It is an odd function. Okay, cos terms are even functions of time. Okay, so this is even functions of time, and the sine are odd functions of time. It is an odd function with respect to time. Okay, so the sine are odd functions. Okay, now what you do, you if this is an even function, cos n omega naught is an even function, we can expect that we have no place for the sine terms in this expression, in the given expression, because when you substitute minus t for t, so in this one you substitute minus t for t, then what will happen? The expression becomes x of minus t is equal to a naught plus sigma n is equal to 1 to infinity a n cos of, it becomes t becomes minus, means minus n omega naught t plus sigma n is equal to 1 to infinity b n sin minus n omega naught t. Now, what is x of minus t? Which is equal to x of t, because x of t is even function, that is what we assumed. A naught plus sigma n is equal to 1 to infinity, cos minus theta is cos theta, a n times cos of n omega naught t, then sin of minus theta is equal to minus of n is equal to 1 to infinity b n sin of n omega naught t. Okay, but this guy is not equal to x of t, right? Let me say this is, let me write x of minus t. Okay, now as per the definition, see I am writing as it is. Wait a minute, okay. Then what will happen? As per the definition, this should be equal to what? x of t. But what is x of t? X of t is a naught plus sigma n is equal to 1 to infinity a n cos n omega naught t plus sigma n is equal to 1 to infinity b n sin n omega naught t. Okay, so let's say this is equation number 2 and this is 1. 1 is not equal to 2, right? As per the definition, x of minus t is equal to x of t, but because of this minus sign it is not equal. When this 1 and 2 will be equal? That is the next question that one should ask. When, at what condition 1 and 2 will be equal? It will be equal only this term is 0. So if these two terms are 0, then x of t is equal to minus x of t is equal to x of minus t. Okay, so if these terms are there, then x of t can no longer be x of minus t. So intuitively we can expect that all bn terms go to 0. Okay, now let's prove this a little more rigorously. Okay, now if we evaluate bn, recall the expression for bn. What is the expression for bn? Bn is equal to 2 by t naught integral of 0 to t naught x of t times sin of n omega naught t dt. Okay. Now I can also take the limit for the sake of convenience in this regard from minus t naught by 2 to t naught by 2, then x of t times sin n omega naught t and dt, and put t by 2 by t naught. This is my bn, because it is more convenient for us in this context. Now I can break up this integral into two parts. So one is from 2 by t naught minus t naught by 2 to 0 x of t times sin of n omega naught t dt plus okay, let it be 2 by t naught integral t0, what am I doing, 0 to t naught by 2 x of t times sin of n omega naught t dt. Okay, now let me assume this is I1 and the second interval is I2, like this. Okay, now we are going to show that this I1 will be exactly negative of I2. Okay, let us prove this. Therefore bn will be 0. To do that, let me take the I1 and let us do. Our goal is now to show that I1 is the negative of I2. Okay, so to prove that, let me evaluate I1 separately. So what is I1? I1 is equal to 2 by t naught integral of minus t naught to 0 x of t sin n omega naught t and dt. Now in I1 I will put x equals minus t. Okay, in this expression you substitute x equals minus t. I will change the variable of integration. Okay, so instead of t use x here. So dx is equal to minus dt. Okay, since the variable of integration is integration now is x, so I must put the appropriate limit also, right? So when t equals minus t naught by 2, then x equals plus t naught by 2. This is the lower limit. What is the upper limit? When t equals 0, then x of course equals 0. Okay, will be 0 because there is no minus 0 here. Okay, let it is x equals 0. Then you replace in the above expression. So 2, it's after all I am changing the dummy variable, that's it. Okay, so t naught, then integral of the limit is now 0 to t naught by 2, x of t becomes I am sorry, maybe I will change the some other variable. Let me say instead of x, because already I have x of t, so I will put some other variable tau. Let us say tau equal to minus t, d tau is equal to minus dt. Then when t equals minus t naught by 2, then tau equals t naught by 2. X of minus tau sine of n omega naught minus tau, then minus d tau. Okay, sine minus theta equal to minus sine theta. So this minus and that minus will get cancelled. So 2 by t naught, integral of 0 to t naught by 2, x of minus t naught, right? By the way, this is minus t naught by 2, and this also minus t naught by 2. X of minus 2, because it's we are assuming even function, right? Therefore, because of that, x of minus tau is equal to x of tau sine of n omega naught tau and d tau, and here is one minus sign and this minus sign, minus 1 times minus 1, it becomes plus 1. So okay, now if I interchange limits of integration, then I will get another negative sign. So minus 2 by t naught, integral of minus t naught by 2 to 0, x of tau sine of n omega naught tau d tau. So this is what I get now. For now I1 is equal to, for even function. Okay, after all tau is a dummy variable, right? Dummy variable. Again I will bring back to t now. So minus 2 by t, integral of minus t naught by 2 to 0, x of t sine of n omega t times dt. This is I1. Okay, this I1 will be minus of I2 now. Okay, so if you look at the previous expression, then this is minus I2. Where is I2 here? Look at here, this one. Okay, minus t naught by 2, one second, which did I took, which did I take? I did a mistake. Wait a minute. Okay, I am sorry. When I substitute the limit, I did a mistake. See, the lower limit is t naught by 2. So why did I put like this? 1 minute. Some mistake I have done. Only in the limit substitution I have done some mistake. Okay. Now, if you look at what is the lower limit is t naught by 2, upper limit is 0, and again here also lower limit is t naught by 2, upper limit is 0. Then this is 0 to t naught by 2. Now if we change the interchange the limits, and what is this? Minus 2 by t naught, 0 to t naught by 2, and this one is equal to minus I2. Why? you can look at here. So I2 is here 2 by t naught 0 to t naught by 2 x of t sin n omega naught t dt. This is your I2. So this I2 will be the similar to minus I2. Therefore, if you expand your Bn is equal to minus 2 by t naught, this is my I1, I am writing as it is, integral of 0 to t naught by 2 x of t sin n omega naught t dt plus integral of 2 by t naught 0 to t naught by 2 x of t sin n omega naught t and dt, and this and that will get cancelled because of this minus sign. Okay, so now this integral is exactly the same as I2, but with because of this minus sign, these two integrals will vanish. Okay, this is a definite integral. So the abstract of this analysis is that Bn is equal to 0. So if the function is even, we immediately can conclude that all sign terms are absent. All sign terms are absent. No need to consider the sign terms for even function. So this is the thing we need to remember. So this is the result that we get if the function is even. So normally we would like to ask, what is the corresponding result for odd function? Okay, how does an odd function look like? What is the corresponding result for an odd function? If the function is odd, we know the definition, x of minus t is equal to minus of x of t. For example, the odd function looks like this. Okay, or if you want to take some simple example, still some very clear example, let me draw it. So you have positive ramp and here you have the negative ramp like this. So this is an example of odd function, and again it comes down, it goes like this, then goes like this, and it repeats forever. Okay, then like this, it repeats, comes down, then goes like this, comes down like this. It's an odd function. Now over one period this is an odd function. So whatever sequence of values it takes in the positive direction, this one, the same value takes in the negative direction also. Now if you again look at the general expression for the Fourier series, we observe that, like let me write down the series first. X of t is equal to a naught plus summation n is equal to 1 to infinity a n cos of n omega naught t plus sigma n is equal to 1 to infinity b n sin n omega naught t. Okay, now if the function is an odd function, we observe that these are the terms which give rise to odd character because of the sign term. Okay, and these are the terms which gives rise to even character. Therefore, if we change t to minus t, we would like the entire function t to minus t, then we would like to have x of minus x of t. That means what? Minus of the whole thing has to come here, that is a naught plus sigma n is equal to 1 to infinity a n cos n omega naught t plus sigma n is equal to 1 to infinity b n times sin n omega naught t. That means a naught should be negative, this whole thing should be negative, and this also should be negative. But in reality what will happen? Your x of minus t is equal to a naught, anyway it is a constant, plus sigma n is equal to 1 to infinity a n cos of minus n omega naught t plus sigma n is equal to 1 to infinity Bn sine of minus n omega naught t. Now, what is the result? Again this is a naught plus cos theta is an even function. So, n is equal to 1 to infinity a n cos n omega naught t plus, not plus, minus, because of the oddness of sine function, sine minus theta equal to minus sine theta, sigma n is equal to 1 to infinity Bn sine n omega naught t. Now, let us say this is here all terms are negative in 1 and in 2 only one term is negative. So, who is spoiling the property x of minus t equal to minus of x of t? This guy is spoiling and this guy also spoiling the oddness. Okay. So, therefore, if I change t to minus t, we would like the entire function value to reverse its sign, but only one term is reversing, remaining all the terms are not reversing. Okay. So, the terms a naught and a n will have the same value for minus t and plus t. Consequently, these two guys, this a naught and a n, these two guys spoil the character of odd function. Okay, it spoils the oddness. Therefore, odd character. We expect those terms be absent. Therefore, these guys, these first two guys expected to be 0. Then your x of minus t is equal to minus of x of t, no problem. Therefore, for odd function, your Fourier series x of t is going to be summation n is equal to 1 to infinity Bn sine n omega naught t. That means no need to calculate a naught and a1, don't waste your time. Just look at the waveform and find out whether the waveform is even function or odd function. If it is odd, don't spend your energy, don't spend your time, simply find out Bn, that's it. And again you can prove this mathematically, okay, rigorously by the same method. Okay, so I will leave this as an exercise for you, okay, to show it. It's very simple, the same procedure you can follow it. Therefore, the result is a naught is equal to 0 and a n is equal to 0, both are absent. A naught and a n are absent, they are 0. So, when we see a periodic function which is an odd function of time, we do not have to spend time in evaluating a naught and a n. Even if you do that, finally you will end up with a 0. So, we immediately know that they are 0. So, all we have to do is work out the value of b of n. Okay, so, this is the end result of odd function. Now, the third type of symmetry is called something called halfway symmetry. Halfway symmetry. Okay, so this third type of symmetry called halfway symmetry is quite important because it comes up in several occasions. Okay, this several occasions. So we will see this halfway symmetry. Basically, what it means is that if you have a particular variation for half the period, then succeeding half the period will have negative of that variation. Suppose if I have the variation like this for half the period, then next half the period it will be negative of that, like this. This is called a halfway symmetry. And I am sorry, let me draw it clearly. Let us say this point is t naught by 2 for half the cycle, then for next half cycle it will be like this, and for next half cycle it will be like this. For every half cycle it is negative of the positive cycle, positive half cycle. Okay, so the sign is going to be changed. This is called a halfway symmetry. Even it not necessarily to be a square wave, it can be any shape. Let us say you have the shape like this, then the same shape with a negative sign like this. Again it goes like this, like this. See, this area will be exactly negative of this area. Such waveforms are quite common, particularly in electrical machinery, okay, where you may have a rotor rotating and inducing the waveform in the stator or whatever it is. Then alternatively, the conductors come under the north pole and south pole, and whatever sequence of values for the electromagnetic field are induced when north pole is in operation, the values will be reversed when the south pole is under operation. Let us say this is under north pole, I do not know, and this will be under south pole or vice versa. Therefore, the waveform exhibits this kind of symmetry. The same set of values reproduced with a negative sign. Here this all are positive, and the same shape, same values will be reproduced with a negative sign here, like this, negative sign. Now, what is the consequence of this waveform? This is x of t and time t, and this point is t naught by 2 for this waveform, and this is my t naught, and let us say this is 3 t naught by 2, and so on and so forth. First of all, we observe immediately that since the same set of values are occurring with a negative sign in the succeeding half cycle, the average of the function over the complete cycle must be 0. See, suppose you find the area of this guy, let us say a1, and this one minus a1, right? It is just reverse. Therefore, if you find the total area of these two guys, a1 minus a1 is equal to 0. So, what is your a naught? A naught is a total area under one cycle divided by t naught. So, if the total area is 0 means automatically a naught turns out to be 0. Okay. So, no need to calculate a naught, which means if a naught is equal to 0 means what? DC is 0. DC value is 0 in this half-wave symmetry waveforms. Okay. This may not be evident, but let us work them out. No, sorry. What are the other conclusions you can draw from this? That you may not, that may not be evident. Okay, let us work them out. Okay, what are the other consequences? Suppose I would like to find out an. So, you know the formula 2 over t naught integral of x of t times cos of n omega naught dt, then the interval is 0 to t naught. This time I break the integral for convenience, like 2 by t naught 0 to t naught by 2 x of t cos of n omega naught t plus integral of x of t times cos of n omega naught t dt. I break the integral into two parts, t naught by 2 to t naught, like this. In the previous one I took minus t naught by 2 to plus t naught by 2, but here I have taken 0 to t naught by 2 and again split into two intervals. Now, let me call this guy is I1, integration 1, and this is integral 2. Now, we would like to relate this I1 with I2, how I1 is related to I1 is related to I2. Let us see. Again, let us take I1. I1 is equal to 2 by t naught 0 to t naught by 2 x of t cos n omega naught t and dt, right? Now, let us substitute, let us say tau is equal to t minus t naught by 2. Now, what is d tau? D tau is equal to dt. here the variable of integration is tau. When what is the lower limit? When t equals 0, then tau equals minus t naught over 2. Hold on. Okay, so let me take I2 instead of I1. Let me take I2 so that it will be easy. Even this also you can show, but anyway, let me take I2. Okay, so this is 0 and this one like this. That's it. Now what is I2? I2 is the lower limit is t naught by 2 and the upper limit is t naught. So the lower limit is when t naught equals t naught by 2, then what is tau? Tau equals 0. Similarly, the upper limit is when t equals capital T naught, then tau equals t naught by 2. Either way I can show, but let me work on it. Therefore, this is equal to 2 by t naught integral of x of t minus t naught by 2 times cos of n omega naught times tau plus t naught by 2 multiply d tau. What is the limit now? The lower limit is 0 and the upper limit is t naught by 2. Okay, now this is the integration that we got now. Now from the halfway symmetry, what is this? If you look at the waveform, you'll come to know. The waveform goes like this. Like this. This is t naught by 2. If you shift by t naught by 2 to the right hand side, then this becomes the same waveform, but it is negative. Therefore, this is 2 by t naught, integral of 0 to t naught by 2. If you shift by, this is my x of t. Okay, you shift to the right, then what happens? Then you will get x of t with a negative symbol. Okay, instead of positive, I am getting negative. Therefore, minus of, this is tau actually, minus x of tau, then cos of n omega naught tau plus before that omega naught times t naught by 2. What is this? This is equal to omega naught is equal to 2 pi f naught times t naught by 2. This 2 and 2 will get cancelled. Then pi times f naught, what is t naught? 1 by f naught. This and that will get cancelled. So only you left with the pi. So here let me write down n omega naught t naught over 2 like this, then d tau. So the same expression I can write 2 over t naught 0 to t naught by 2 minus x of tau cos of n omega naught tau plus n pi. Okay, so this is your I2. Now what is the value of I2 now? This minus sign you can take outside, 2 by t naught 0 to t naught by 2 x of tau cos of n omega naught tau times n pi, right? So this is my I2. You substitute back in the previous expression. Where is the previous expression? It is here. You substitute back here. So this is my an. So therefore an is equal to 2 by t naught integral of x of t cos of n omega naught t dt, and what is the limit here? 0 to t by 2. Okay, plus I2. What is I2 here? I2 is this guy, minus 2 by t naught integral of 0 to t naught by 2 x of tau cos of n omega naught tau plus n pi. Okay. Now after all, this tau is a dummy variable, you can change to t. Therefore an is equal to 2 by t naught integral of 0 to t naught by 2 x of t cos of n omega naught t dt minus 2 by t naught 0 to t naught by 2 x of t cos of n omega naught t plus n pi times dt. Now you substitute n equal to 1, n equals 1, n equals 2, n equals 3 and so on. Now when you substitute n equals 1, then what happens? Right? If you substitute n equals 1, then cos of n omega naught t plus pi, that is minus value. Okay, I have done somewhere mistake. Where is it? Yes. Okay. When n is equal to 1, let's say when n is equal to 1, 3 and 5, then what happens? This becomes minus of like pi, 3 pi, 5 pi like that. So this is minus of n omega naught t for n is odd. Okay, minus into minus plus. Okay, so for n is equal to odd, your an is equal to n is equal to odd. In that case, an is equal to 2 by t naught 0 to t naught by 2 x of t cos of n omega naught t dt, and here you will get minus and this minus, both minus will become plus, minus times minus. So 2 over t naught 0 to t naught by 2 x of t cos of n omega naught t dt. Okay, therefore this is the same as this guy. So 2 times 2 by t naught 0 to t naught by 2 x of t cos n omega naught t dt, that is your for n is odd. Therefore an is equal to 4 times t naught 0 to t naught by 2 x of t cos n omega naught t dt. So this is a formula. In case if n is even, then what will happen? This one is even number, n is even, then 2 pi is 0. So that means you will get again cos of n omega naught only. So this n pi will not have any contribution for even number of values. So already have minus here, and both will get cancelled and it becomes 0 for even number of n's. Therefore an is equal to 0 for n is even, and this one is n is odd. Okay, so the final result is an is equal to 0 for n even and 4 over t naught integral of 0 to t naught by 2 x of t cos of n omega naught t dt for n even. So the same analysis can be done for Bn terms also. So you can show that Bn will be 0 for n even and 4 over t naught integral of 0 to t naught by 2 x of t sin of n omega naught t dt for n odd. So this is the result. These two formulas you should remember. Okay, so all even ordered harmonics are present. The final point is all even ordered. Don't confuse with even function and odd function. This is even order. That means what? N is equal to 2, 4, 6 like that. All even ordered harmonics are absent. That means A0 is 0, A2, A4, A6 is equal to 0. Similarly, B2, B4, 0. B6 is equal to B8 dot equal to 0. So when you have this kind of symmetry, half-wave symmetry, as you have in the waveforms generated by electrical machines, you will have only the fundamental component. Third fundamental component means what? Omega naught, that is A1 and B1, then A3 and B3 third harmonics, then A5 and B5 fifth harmonics, and then A7 and B7 seventh harmonic. These are the terms that are going to be present in your waveform, and all even ordered harmonics. Okay, not even function or odd function, even order. Order means n equal to 1, 3, 4, 5 like this. When I say even order, 2, 4, 6, 8 like that. Okay, so you cannot think of having the second harmonic in this or fourth harmonic, not even DC term. DC term also 0. A0 equal to 0, because the average of A naught is going to be 0. So for the calculation of odd harmonic components An and Bn, instead of taking the integration over the complete period, generally how will you calculate? 0 to t naught. Don't do this 0 to t naught, just to do it, don't do this. You just do from 0 to t naught by 2, that's all. Okay, so it is permissible for us to integrate over half the period, and consequently how you don't have 2 by t naught, but you have 4 by t naught. Don't forget. That means you are taking the twice the average over the half the period rather than twice the average over the complete period. So you can also dispense with a lot of integration. Okay, dispense with a lot of integration work because of this property. So we always love to use this property in order to simplify our work, make our life very simple. And confine yourself to one half cycle. Okay, only look at only half cycle whenever you have this kind of symmetry. And the important point is that all your even harmonics are absent, and DC component are also considered to be even harmonic, that is also absent. Okay, so you cannot say DC is like not even harmonics. So again, that also considered to be an even harmonic. Now let us look at the last type, that is last type of half-wave symmetry. There is no name for this. Let's say another kind of half-wave symmetry. Okay, so in this one, x of t is equal to x of t plus t naught by 2. Okay, previously what we said in the previous case, we said x of t is equal to minus x of t plus t naught by 2, but here we are saying it is plus. Okay, so let's say your waveform is like this. Let me draw nicely. So the waveform goes like this. Instead of going like this, your waveform goes like this again. Okay, it goes like this. So it is not going in the negative direction. Like this, the waveform is going like this. Let us say this is x of t, and this point is t naught by 2, t naught, 3 t naught by 2. The negative side also it goes like this. Okay, like this. This is minus t naught by 2, minus t naught, and so on and so forth. Now, strictly speaking, we should have t naught by 2 as the period, not t naught, because we agreed period is the smallest value which satisfies the condition x of t is equal to x of t plus some capital T naught. But strictly speaking, this should be the period, right? But in this case, we are taking this as the period t naught. Why? We will see why we have taken like that. Basically, t naught by 2 is the period, which means the frequency of this is this one. What is the frequency? F naught is equal to 1 by t naught. Okay, if you consider this as the one period, then frequency is equal to 1 over t naught. Okay, but as per the definition, what we said? We said the least value is called a period. Let us say if I take this is period t naught by 2, then what is the frequency? Frequency is equal to 1 over t naught by 2. This is 2 by t naught, which is 2 times f naught. Now, which one should I take as a frequency? I should take this one, figure 1, or figure 2. Which one should I consider? As per the definition, I should consider this one only. The smallest positive value is called a period of the periodic signal. Okay, so here only what I call even ordered harmonics are present, and all odd ordered harmonics are present because there is no negative cycle. Now, naturally, you ask a question, why do you make a big fuss about this instead of considering this as a period? See, actually speaking, this as the period, but what are we doing? We are taking this as the period. Why? That is what we are asking now. Why? The smallest value I am supposed to take period, this as the period, frankly speaking, but I am considering this guy as the period. If t naught by 2, this one is the basic period, why not call that as the basic period, this one as the basic period, and call that t naught as the period. Now, we are calling t naught as the period in our example, in the fourth example. The answer to this question is, often we may have a particular waveform which we split up into number of components, number of other waveforms. So, you may have some original waveform, in the original waveform has the period t naught, and from this we construct some other waveform, and in some other secondary waveform, okay, in that secondary waveform the period is it happens to be t naught by 2, but we are saying here that here also the period t naught with respect to the original waveform. So, therefore, this is not a original waveform, this is some other waveform. If I take an example, you will understand very better. Okay, you can understand much better. This is not a original waveform. With respect to original waveform, this is the period. Of course, if you take this waveform as it is, then t naught by 2 is the period, no doubt in that. The original waveform we split up into number of component waveforms, and in one of the component waveforms, see like that I can have secondary waveform, then another third waveform, there it may be something different. So I can have many waveforms, but I am speaking this t naught as a period with respect to the original waveform. Okay, so I think you might have studied about half wave rectifier. Recall your half wave rectifier. Now in the half wave rectifier, what happens? You will give a sinusoidal signal like this. The moment you rectify, let's take full wave rectifier, not half wave rectifier. Let us take full wave rectifier. So then the waveform looks like this. Then what is the period? Say this is t naught, and therefore this has to be t naught. You cannot say this is t naught. You cannot say. You cannot say that period is. You cannot say that period is t naught. Here this has to be t naught by 2 and this has to be t naught. So this t naught and t naught by t by 2 with respect to the original waveform. This is my original waveform. So with respect to the original waveform, my period is t naught. Okay, with respect to original waveform, the period is t naught. These days more number of people are flying, it seems, to Tiruchirappalli. Okay, fine. So with respect to the original waveform, the period is t naught here in this one, okay, not t naught by 2. But in case if you take the waveform like this without considering the original waveform, then of course this is the period, no doubt about it. Okay, so whatever the frequencies present in the original waveform, we would like to relate the fundamental frequency of the original waveform. Consequently, we still have this t naught as the basic period, even when you are dealing with the secondary waveform, rectified waveform, full wave rectified waveform. So in this context, if you persist with it, calling t naught as the basic period, then you can have even ordered harmonics and odd ordered harmonics are present. Okay, so the fundamental will not be present naturally because it is first harmonic. Okay, so we will work out an example later which will illustrate this. Okay, so this is really matter of definition. So in this case, when you say x of t is equal to x of t plus t naught by 2, then your an is equal to like 0 if n is odd and 4 by t naught integral of 0 to t naught by 2, no need to consider up to t naught, x of t cos of n omega naught t, and bn is equal to again 0 if n is odd, all odd harmonics are absent here, and 4 over t naught 0 to t naught by 2 x of t sin n omega naught t dt. This is exactly reverse of what we studied in the previous case. Look at here, for n even it is 0 and for n even it is 0. For odd you have the non-zero values 4 by t naught. For odd you have non-zero value, but here for even it is non-zero value. Even n, this also for even n. So this is for this kind of symmetry. Now if you have x of t is equal to minus x of t plus t naught by 2, then an is equal to, just I am repeating here the previous result, 0 if n is even and 4 over T naught if n is odd. Sorry, the complete expression is not, I didn't write. 0 to T naught by 2 x of t cos n omega naught t dt if n is even. Similarly, for Bn, again 0 if n is even, odd, n is even, and 4 over T naught integral of 0 to T naught by 2 x of t sin n omega naught t dt if n is odd. That's it. Now, when we were discussing the first chapter, when we were discussing about a signal part, that time we said an arbitrary signal can be written as x of t plus even part of x of t plus odd part of x of t. Please recall the definition. Any arbitrary signal can be written in terms of sum of even part and odd part. Okay, because some signals may not be neither even nor odd. If it is periodic with even function, okay, no problem, you are done, your life is very simple. Sometimes the signal is periodic with odd signal, then also no problem, fine. If it is even symmetric or half symmetric, no problem. But sometimes this 4 for the given signal will not fall under this 4 category. Okay, sometimes the signal x of t will not fall any one of the aforementioned 4 category. Then what you do? Then there will be a problem. So any arbitrary periodic function may not be even by itself, may not be odd by itself, neither even nor odd. So in that case, what we can do is we can generate from it the even part and odd part, but you can separate into even parts and odd parts. Therefore, x of t can be written as the even part of the signal plus odd part of the signal. Now we got the formula also for even part. What is the even part? Even part of x of t is equal to x of t plus x of minus t by 2. Similarly, what is the odd part of the signal? X of t, x odd part of the signal is going to be x of t minus x of minus t divided by 2. And this is the even part of x of t, and this guy is the odd part of x of t. That's it. So from any given function, arbitrary function which is neither even nor odd, you can generate its even part and odd part by this method. Naturally, the Fourier series of this will contain only DC terms. This even part, this guy contains only DC part and an, and this guy contains only bn. Therefore, for an arbitrary signal you can split like this, and then you can work out what is a naught, what is an, and what is bn. Okay, so whenever you have a composite signal, then the Fourier series can be written as like for even part, that corresponds to a naught plus sigma n is equal to 1 to infinity a n cos n omega t, and for this odd part it corresponds to bn sin of n omega naught t. Okay, and it might be possible for us in some situations to break this up into even part and odd part when the signal is neither even nor odd, and also find some additional symmetrics in their respective parts also. Okay, so we will work on it maybe in the next class. So with that, let me stop. Okay, thank you very much.